Hey, welcome back to integration of trig functions, and this course presumes that you have already done the basics of integration with algebraic functions. We're just going to extend it now. So from what we've already said, the big question with integration is what is the rule to be reversed, because in integration that sum of an infinite number of rectangles' areas came down to using an area function whose derivative was the given function. So we had to go and undo the derivative, anti-derivative if you like. And so we've got to, first of all, if we're going to undo it, we've got to say, well, what rule could have produced this? And here's some over here that we've already looked at in the previous presentation. Going backwards, increasing the power by 1, dividing by the new power. Don't forget the constant of integration there. That's just telling us there that there's a whole family of functions which, when differentiated, we give that original one, okay, because the derivative of a constant is 0. So all of these now you are expected to know, and let's now try to extend it and look at some rules, other rules that we need to reverse to find the integral. Okay, and here's some over here, and we're going to start with those in a minute. They are linear functions and then a power, or e raised to not x but a linear function in x. Okay, and then the ln one, 1 over, what function produces a reciprocal like that on differentiation? It's log ln. Okay, so we're going to go and reverse all of those now, and here's some interesting ones down here. I wonder how you could get a product here from a process of differentiation. What rule produced that? We want to go backwards now. So conceptually, in this presentation, it's fairly straightforward. It's what's the rule to be reversed, and we have to be careful there. And here, maybe this product is a bit different from the other one. I wonder if you can see why. Anyway, let's get going and build up some more skills in integration of trig functions. So here we are. If you look at the function ax plus b to the n, it's a function of a function in x. So first of all, let's deal with the n. Increase the power by 1, divide by the new power. This is reversing a function of a function rule where you have a linear function in the second place. And we have to divide by the derivative of what's in here, the ax plus b. Because when we differentiate this, we do the power first and then multiply by the derivative of that function inside. So we've got to do the reverse there. Just noticing plus c, and also n cannot be neg 1, because we would be dividing by 0. So we'll come across that. That's going to give us our log example in a minute. Okay, just realise that ax plus b to the neg 1 is 1 over ax plus b, isn't it, that negative exponent? And of course we know the rule for that. That's down here. If you had one of those, you wouldn't use reversal of the x to the n rule, because you know that's come from applying the log function. And of course we've got to put these absolute value signs in here, because you can't find the log of a negative number. Let's have a look at the graph of the log function. Looks like this, doesn't it? And you can't have the log of a negative number. So we're going to say we can reverse this rule and use logs as long as it's going to be a positive in there. So we ensure that by putting the absolute value or modulus sign there. And of course we've got to divide by the derivative of ax plus b. Because on differentiation we will multiply by it. And same thing here. The function of a function here. It's the e function done on a linear function. So let's do the e part first. The function which when differentiated gives e is e itself. It's the same, isn't it? So it's e ax plus b, and then we have to divide by the derivative of that linear function, reversing the two aspects of the chain rule. And of course plus c everywhere. And you could always check this. Let's just check one here to see if you can realise what's going on. Let's check the integral of e to the ax plus b, that one, and we've said it equals 1 on a e to the ax plus b plus c. So let's differentiate this. let's find the derivative of that and see if it does give us that e to the ax plus b back again. All right, so we've got the derivative of 1 on a, e to the ax plus b, derivative of e is itself, and then times by a. So that's a chain of derivatives. Derivative of a constant is 0. Now we've just applied the chain rule because we realise there's a function and there's a function. Oh, that's why we had to divide by the a, so that we cancel that out and just get e to the ax plus b. So just notice that. You can always do that. When you've integrated, you can check it because on differentiation, that should give us the original function back again there. So the cos, what is the integral of cos? It's sine. Okay, but you've got a function in here, so you've got to divide by the derivative of that function. Reversing the chain rule. The integral of sine is neg cos, so we've done that, but we've got to divide by the derivative of what's inside there. Realising that that's the rule that would have been applied. So sec squared, when differentiator gives that, it's the tan of ax plus b, but then dividing by that and plus c. Okay, are you ready? Let's have a go at some basic ones here, some screen clippings from Hayes and Harris publications. You should have their book handy by there. Okay, integrate e to the neg 2x, take 4 sec squared 2x. What is the rule that has been used to produce that? Okay, so we're going to put the thing down in full with a dx, nicely presented. Now, integral of e, when differentiator gives e, it's itself, same power, nothing changes. Normally we multiply by the derivative of that other function. Now we must divide. So it's 1 over neg 2, the derivative of the neg 2x term. And when differentiator gives sec squared, it's tan 2x. And then we have to divide by the 2. We've got 4 lots of it, so that just stays out the front. And then don't forget the plus c. So then we can tidy it up here at the end, because 4 times a half is 2. What about this creature over here? Same thing. Set it up nicely with the integral sign and naming the variable with respect to x. That's naming the variable. So the 2 stays out the front. When differentiator gives sine, it's neg cos. Okay, because the derivative of cos is neg sine. Okay, so it's neg cos 3x, and then we have to divide by the derivative of this other function, because we see this is a function of something which is a function in x itself, 3x. And then integral of cos, when differentiator gives cos, it's sine 4x. And then we have to divide by the derivative of this function in here. And then we can tidy it up at the end. Don't forget the plus c. Okay, what is the rule? That's the question. What produced this derivative? And we're going backwards. Fairly simple conceptually. We've got to be tricky with our rules though. So here we are, 7d2. Have a look at that. There's a little hint here that because tan squared is not a derivative of something directly, you might use this identity. 1 plus tan squared equals sec squared, or tan squared is sec squared, take 1. Because instead of integrating that, we could integrate this expression. And what's the advantage? Well, we know sec squared is a derivative. It's a derivative of tan. Okay, so we're changing the problem around to more easily identify the rule to be reversed. So could use that later on. All right, pause the presentation, have a look at these, and the answers are down below. All right, let's go and have a look at them. Those half a dozen parts there. 9 parts actually. Okay, so check these. Don't forget the C's everywhere. It's going to be a mark if you leave that out. Okay, very important concept there, that the derivative of a constant is 0. Okay, let's keep going now and try and build up some more skills. Now, this next batch is a little bit different because you've got to do something to the function before you try to reverse the rule. Because tan squared is not the derivative of anything. And no rule, when applied, will produce that. So let's change it to sec squared, take 1, like I just said before. All right, because the function which when differentiated gives sec squared is tan. So the integral of sec squared is tan. The integral of neg 1 is neg 1x, and then plus c. Okay, so we're going to try and get it into a form where we can identify what rule has been applied. And this is 1 over, so that'll stay there. And we name our identity here, so we've got sec squared take 1 for tan squared. Now, the integral of sec squared, what function differentiated gives sec squared, is tan 2x. And then we would divide by the derivative of that function. And then take x to get a 1, and coefficient of x would be neg 1 there. So on differentiation you get that neg 1. And then here now integrating 1 on that, what function when differentiated gave that? It would have been ln. And putting in the absolute value sign to make sure the function is going to be positive. Okay, and then we have to divide by the derivative of this. Let's keep in mind, this is a function, it's a reciprocal function of the linear function 1 on 2x, 1 take 2x, sorry. Okay, and then plus c. And we can put it a bit more neatly here, negative times negative, positive, and so on. Okay, so there's some tricks here. To answer the question, what was the rule that was applied on differentiation to get this? We need to reverse it. So sometimes we have to simplify the expression to identify the forms. Okay, come down and you can have a go here in a minute. There's just a little bit here about sine squared plus cos squared is 1. If you divide everything by cos squared, you get this. And 1 on cos squared, 1 on cos is sec, so 1 on cos squared is sec squared. So this is a proof that tan squared plus 1 equals sec squared, or tan squared equals sec squared take 1. So that's going to be important here. Right, get the idea. If you look at something and say, gee, I don't know what rule would have produced that, then maybe we can take a look at the function, arrange it, rearrange it, use a formula, and see if we can identify what rule has been applied. Okay, pause the presentation, have a go at each of these. That's important. Don't forget, function of a function. Have to divide by the derivative of that second function, reversing the chain rule there for a linear function. Okay, I'll show you the solutions now. Come down here. There's some nice solutions for you there. Okay, let's move on. They get more and more interesting, and if you've done sister subjects where you've done integration of algebraic functions, I think you can see some of the things we might have to do. All right, now here are two identities that are extremely important here, because like with tan squared, we can't integrate sine squared. It's not obvious what would have been differentiated to give that. Okay, so we're going to use the identities. Cos 2 theta equals 1 take 2 sine squared theta. And if we rearrange that, and I'll do it for you here, cos 2 theta take 1 equals neg 2 sine squared theta, or sine squared theta is a half take a half cos 2 theta, dividing through by neg 2. That's where that one comes from. So that's handy, because if we get this thing, it's not obvious what rule has produced that, so we can't undo it. And this one over here comes from 2 cos 2 theta equals 2 cos squared theta take 1, and rearranging that similarly. So that's going to help us integrate cos squared, isn't it? Because we can use just this, and that is integrable. We can see where cos came from. The integral of cos is sine. Okay, so let's have a look at one. Here's a function here. Now, the square of 2 take sine x, could that be produced by a single rule? No. We wouldn't see the rule there, so let's expand it. And we've got this, remember, a take b all squared. You need to have all these skills. Remember, a Huddyism is that maths learning is sequential and cumulative. And when you learned that way back earlier, you're now expected to pull that out and use it with trig functions. Accumulate your knowledge. Okay, so let's have a look at this. A squared, 2ab, and b squared if you like. Okay, so now this poses the only problem, so we'll change that to a half take a half cos 2x. And now we can put these two together as 4.5 or 9 over 2, and then the separate terms. So let's integrate the constant. Okay, so that means it was the coefficient of x to get 9 over 2 left. That's the x to the n rule, where you've just got 1x, 2x, etc., constant times x. And get rid of that. And then we've got the integral of sine here is minus cos. So that becomes a plus, and the 4 just comes down. We've got 4 lots of that function. We've got 4 lots of its integral then. Neg-1/2, and the integral of cos is sine 2x, but we've got to divide by the derivative of that function in there. We're reversing the chain rule. Okay, and then plus c. So we can tidy it up a little bit. Neg by neg is negative times positive is negative, and half by half is a quarter. Okay, are you ready? You've got to be a little bit tricky here. It's not a concept or an idea that's hard. It's being tricky and trying to identify what's the rule that's being used to produce this. Don't know a rule, don't know a rule, don't know a rule. Going to have to play with this. Okay, and here they give you some hints. Sine to the 4th, that's interesting. Okay, so you can use the same sort of thing there. So please remember, it's a simple concept. What has been done, what rule has been applied to a function to produce this as a derivative? We've got to undo that differentiation. Okay, so don't jump in and do silly things, ask the question. And if there isn't a direct answer, you've got to play with the function and simplify it. Okay, pause the presentation. You should have a go at most of these, so you're getting the hang of it. I'll show you the solutions now. Okay, 3 and 4 there. Hope you're going well. Might have to go back over it and suss it out a bit. Let's move on now. Okay, here's some more formula we've seen before earlier in this course, usually in the earlier year of this course. And what is this? This is showing you how to change a product to a sum or difference. Okay, and you'd read this, 2 sine A cos B is sine of the sum plus sine of the difference. Cos is cos of the sum plus cos of the difference. And sine is cos of the difference minus cos of the sum. So those words that I just spoke of then are a generic interpretation of what A and B are really standing for. Any two angles. Okay, so the generic interpretation, the word interpretation, helps you not make a mistake when you're applying these. So there's a hint, we're going to have to do that. Let's come down and have a look and see how we could determine that. Okay, show that sine x cos x equals that, and hence find that. Well, why did they give us this clue here? Well, when we look at this, we say, what rule produces a product like that? Well, a chain rule can, because you differentiate the first function, then multiply by the derivative of the second. So maybe it is possible to get that product, but is this the derivative of that or vice versa? No. So that's a chain rule test, and we're going to do that in a minute. The chain rule test that we would apply to any product or quotient. Okay, we'll have a look at that in a minute. You should have seen that in the other course that introduces integration in algebra, in algebraic functions. So here we are, let's play with this. It is sine cos, so it's a half, because it produces a product, the sums of product to sums and differences has a 2 in front. So we haven't got a 2, so we're going to say it's half of 2 times sine cos. We're trying to make it fit the pattern of this and fit it in to the products and sums and differences formula that we saw above. So sine cos is sine of the sum of the two angles plus sine of the difference of the two angles. Always in that order. X is the first, 4x is the second, so it's 5x plus sine neg 3x. And we've gotten out of the difficulty of determining what rule has produced that product. We've changed it to a sum of two functions, and we can say here the sine of neg 3x is minus the sine of 3x. If you want to make it that way, you can just leave it as neg 3x if you like. But anyway, we had to here show this, remember? They gave us that hint. So now with the integral of this product, it becomes the integral of a difference, and that's easier. So we've got half of that, so it stays out the front. Integral of sine is neg cos, leaving this unchanged, like the chain rule, and then dividing by the derivative of 5x. Same here, neg half out the front, and now the integral of sine is neg cos 3x, and dividing by the derivative of that function in there. You must identify the rule, there it is. We must identify the rule, and when we're down here, these rules that we're looking for are here, the chain rule, and you divide by the derivative of that second function, the 3x. And then don't forget the c every time. All right, your turn to play with these formulae, which is products of sums, differences formulae. Okay. Right, well, I want you to have a go at each of those. There's a mixed bag in here. Okay, you're going to have to go back and do some of the things you did before and see what you can make of it. And you might have to be careful with this one down here. Okay, I have to think about that one. Okay, if you can't see an actual rule that's been applied, you have to manipulate the function, simplify it, so that you can identify what's gone on. Be careful with that one. Okay, you've had all the identities we need, but you might just be careful there. All right, let's go down and look at the answers now. Okay, did you get 6F right? Okay, you might have to think about that one. There's a couple of rearrangements you have to do there. I hope you didn't try to use log. Oh, no. Have to talk to your teacher and other students about that one. Okay, let's go on, and we're nearly at the end. Can you see we're retracing all the rules of differentiation? Ah, here it is. Look at this. That's a product. Would you try to use the sums and products formulae for that? No, because the first rule that you try to look at is the chain rule test. Testing to see if maybe the chain rule has produced that. Let's just revise the chain rule now. If you've got, let's say, a function u of v of x, then the derivative is the derivative of u with respect to x, with respect to v of x, and then you multiply by the derivative of v, the function in there. Okay, that's where the rule comes from, isn't it? The chain rule. It's a chain of derivatives. Here there's two. As you might remember from an earlier presentation, I like students to think of it as a function of a function rule. So it makes it easier to identify when to apply this rule of differentiation. So we're going backwards now. So we're going backwards. So what we want to do is see if we can identify a chain rule pattern in the thing that we're trying to integrate. And then we've got the rule and we can reverse it. Remember, what is the rule? Okay, so let's have a look over here. There's something interesting here. Sine is a derivative of cos. Well, not quite. Derivative of cos is neg sine. Hey, we've got the chain rule here. Look, a function of a function and the derivative of that inside function present. I reckon we've hit it. It's the chain rule. What was the rule? It's a chain rule. So the technique here is to say let u be the function whose derivative is present. So u is cos. It's not the other way around. Okay, but I mean here, it could say u is sine x because cos x is the derivative of sine x, but it's not cos x, it's cos cubed x. So there's a function of function, and check out, this is the accompanying derivative. So you let u be, not the whole function, you let u be the function whose derivative is present. And then, of course, we write down du by dx is neg sine x, and then rewrite the integral. So the integral becomes the integral of u cubed neg du by dx with respect to x. And then we write down, that is simply putting the neg out the front, negative the integral of u cubed with respect to u. What we're saying is, this is validation of the chain rule form. Well, this is showing the chain rule form mathematically and saying, well, we don't really have to worry about the dx here. You shouldn't cancel them because they mean a lot more than that. It's talking about limits there. But the idea is we're differentiating or integrating here with respect to x, and we've got the accompanying derivative, so all we have to worry about is the u part of the function, the cos part, okay, not the x part. That's what that's saying here. That's really coming back and identifying the chain rule form and saying, well, therefore we've only got to integrate or reverse the differentiation process for in u-land, which is cos x as the variable. Okay, and so it becomes just reversing the q because it's with respect to u, or cos in this case, as the variable. All right, do you get the idea here? So here it's u to the fourth on 4 and u was cos, so replace the u by cos there. Okay, what about cot x? Ooh, I don't know what would have produced that. Haven't learned that one. So we could call cot cos over sine. Cot is 1 over tan, if you remember. 1 over tan x. So this is cos over sine. Or any quotient should be written as 1 on sine x by cos x. Should write it as a product. Because can you identify the rule? No. No rule produces something as simple as cos x on sine x as a quotient. The quotient rule is far more complicated, isn't it? U dash v, take u v dashed on v squared in a common notation. So this quotient can't have come from the quotient rule. It doesn't look as easy as that. So let's change it and call the quotient a product and apply the chain rule test to that. So what do we find? Cos is the derivative of sine. So start by saying, which is the derivative of the other? Okay, now 1 on sine x is not the derivative of cos x. Derivative of cos x is minus sine x. So here, if you let u equal the function whose derivative is present, so notice the idea of identifying the chain rule is trying to find that part of the chain in your product, or here you've changed a quotient to a product, which is the derivative of the other. So cos is the derivative of sine. So let u be sine, and du by dx is cos. Reconstitute the integral in u-land. So this is 1 on sine x, so it's 1 on u du by dx with respect to x. Now we have identified that this is the chain rule. We realise that this has come about purely because u is also a function in x, and we can ignore that. We can just integrate 1 on u as if it's the variable. As if u is the variable. The integral of 1 on is ln modulus of u, or absolute value of u, plus c. So then you can replace sine x in place of u. We do this so that you can identify clearly the rule that has been applied and that you're trying to reverse, and you're giving him mathematical evidence for that. Okay, it's a pity we don't put here reversing chain rule or something to validate that step further. But you're supposed to be able to see that. Hey, you produced a chain rule, a chain of derivatives here, and now you're going to identify that and reverse the chain rule. All right, it's called integration by substitution. And here, this is unusual. They generally won't tell you this in tests and exams. You'd be expected to run the test for yourself. Is one of these the derivative of the other? Is sine to the fourth the derivative of cos? No. Is cos the derivative of the sine? Yes. Okay, so let u be, remember now, let u be the function whose derivative is accompanying, whose derivative is present. Okay? All right. That's the system. So when you look at anything, and here we're going to say, that quotient, that's a simple quotient. That hasn't come from the quotient rule. I could call that a product. 1 on root cos x by sine x, and try to see if that has been produced by the chain rule. All right. So quotients must be changed and tested. And if that doesn't work, you'll have to use formulas to simplify it. Okay, pause the presentation and have a go. I'll show you the answers now for this one. Okay, so there we go. I hope you're having some success there. Link it up with what you've done in integration of other functions, the algebraic functions, because it's very closely allied, isn't it? Okay, last little bit now. Hang on in there and let's do some more work and come down. Here we go. Last one here. Integrate sec squared tan squared x with respect to x. Now it's a product. So the first thing we'll test to see if the chain rule could have produced this. Is one of these the derivative of the other? Oh yeah. Derivative of tan is sec squared. So let u be the function whose derivative is present. So let u be tan x. Write down the derivative carefully and then set the integral up as du by dx u squared dx, because that's the order in which it was placed. Because you've got the derivative of u with respect to x, you can just integrate the u squared as if u is the variable. That's what that's saying. And then do it. Okay. Let's follow through now with the last little set, question 8. And these are tricky do's. You have to be careful here. There's a hint in part F of how to break it up. And this is the interesting one here. Remember, you're looking for that chain rule pattern where you have a function of a function and then the derivative of that inside function is present. So it's very important that you change quotients to products and then try to identify whether one term is the derivative of the other or the function contained in the other part. You're looking for that now. Okay, have a go at these. You should try all of these. These are more like exam questions now. I'll show you the solutions. Okay, and there's the final answers to that set. And I hope you've had some success there. Here we go. There's one little bit left here, along with the that sort of trick. Integral of sine cubed. We don't have an identity for sine cubed, so we can break it into sine squared x by sine x, and then start playing. Okay, and trying to get it to a point where we can say, is this the derivative of something in here? Yes, it's the derivative of cos, so let u be cos x. Derivative is neg sine x. So now this becomes integral of 1 take u squared, neg du by dx dx. So we've only got to integrate, multiplying through there, u squared take 1 with respect to u. And then increased power by 1 divided by new power, a constant when integrated gives that many times of the variable plus c. Okay, then returning cos there. Okay, so getting some tricks. It is more about trickery here rather than concept. Can you get the function into a form where you can identify the rule of differentiation that produced it and then reverse it, the antiderivative? Okay, let's go down to the last couple here and see what you think here. So they're all different powers and different tricks you need to use to break it down so that you can identify what rule's been applied. Okay, pause the presentation, have a go at all of these, and I'll show you the answers now. Okay, so there's question 9 and 10. If you can do 8, 9 and 10, I congratulate you. You're pretty good now. Okay, Well, guess what's coming up? I think you probably already know. What we're going to do in the next presentation is look at areas, and definite integrals and things like that, the fundamental theorem of calculus again. So I'll see you then. Cheers for now.